Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's my great pleasure to welcome Rob Fergus here today. Rob is a professor at New York University, and he's very well known in the computer vision recognition community for having developed one of the first systems to learn constellation models. He's also done wonderful work in computational photography, aspects of learning with very large data collections, which I think is related to his topic today. And he's on his way up to NIPS, where he'll be delivering a version of this talk.
Thanks, Rick. Yes, so okay, this is a talk that this is some work I've done with Yair and Antonio, what I'm going to talk about today is doing stuff with huge collections of images. Okay, and so there's been some quite interesting work by people in Microsoft here on taking people's holiday snaps from the internet and creating these sort of rich 3D environments from them, and doing all sorts of fun things with your photographs to repair them and so on. And all these approaches are really leveraging the vast amount of data that's out there on the web. But people have been sort of less successful about developing object recognition techniques that we can use on the sort of billions of images that that you have out there now on things like Facebook and these other websites. And so what I'm going to present today is one approach which you could integrate with a variety of different recognition systems that really does scale to sort of large collections of images. Okay, so one feature about the kind of data you find on the internet is that you don't just have this idea of nice clean labels. Often you have this sort of spectrum of label information. Okay, so you have some images which have been manually annotated. You have nice clean labels which you trust, but that's likely to be a pretty small fraction of this giant amount of data out there. What you are likely to have a lot of are these sort of noisy labels where people have some sort of text metadata or something like that, which gives you some clue as to what might be in the image, but you certainly can't trust it entirely. And then, of course, there's also going to be a vast amount of data for which you haven't really no label of any sort. Okay, and what you would like is some approach which can sort of integrate information from all these different sources and do something useful from them. And so the machine learning people, have developed approaches that do this, and which is essentially semi-supervised learning. So I'll just give a brief introduction for those of you who aren't familiar. So the idea is you're given a whole collection of data. You assume that only a very small number of them are labeled. In this case, they're just 2 data points that are labeled. And what you want to do, in the classical sort of supervised setting, you would just take these 2 labels, train your classifier, and try and label the remaining examples. Okay, and so if you do something like nearest neighbor or something like that, this is the kind of thing you end up with. Okay, so the decision boundary is just sort of equally distant between the 2 points. And you can see it's a perfectly reasonable thing to do, but you can see that it somehow doesn't respect the density of the data. And in semi-supervised learning, what you would like is some sort of the label function to the labels to sort of propagate smoothly through the density, so that the resulting labels do accurately reflect the sort of structure of the data that you have. Okay, so the semi-supervised approach that I'm going to talk about today is based on the what's quite a common variety, in fact, that use these graph Laplacians as the basis of the approach. Okay, so the idea is that each image is going to be a vertex in a graph, and you're going to look at the affinities between the images, which are going to correspond to the edges in the graph. And we're just going to have a sort of Gaussian type affinity, which just tells you how far, based on how far apart the images are. It's x being some descriptor we're going to extract for each image. And the thing which we're going to use is this thing called the graph Laplacian. So the idea is here you have this affinity matrix W, and then D is just a diagonal matrix, which is you sum across the rows of W, and then this is the thing that you construct, this matrix L. Okay, so it's a little bit hard to get intuition what that does. So just to get an understanding, what it really is doing is it's going to measure the smoothness of your label function f. Okay, and the idea is if 2 points are close together and they have a high affinity, you'd like the f values of those 2 data points to be very similar. Okay, and equally, if the affinity is small, then the f values can vary to a greater extent. And so what you want, of course, is to find an f that minimizes this quantity here. Now, of course, this has a sort of trivial solution. So if you just have f equals to 1, then, of course, or some, f equals a constant value, then you end up with, this being 0. But, of course, if you bring in the labels from those few labeled examples you have, then you end up with this expression here. So you have something which measures the smoothness of your label function, and then you have something which checks how well your label function agrees with the few labels that you've been provided with. Okay? And so the lambda here is just a weight, which you can think of as being large on your labeled examples and being 0 otherwise. Okay? And if you can then sort of rewrite this in this sort of just as this weight here is just a kind of diagonal matrix. And what you'll then want to do is to find the f that minimizes this expression. So this is a fairly straightforward thing to do. So yeah, just to make clear that the points that are unlabeled have sort of 0 weight in this term, and the ones that are labeled have some fairly large value lambda. So this, Jeff, hey.
Such a line 1D, B numbers of 1D. Those yi's are scalars?
The class label, yes, we're just considering the simple two-class problem here. We're not doing any multi-class thing in this work. Okay, yeah. Okay, so finding the minimum of this is fairly straightforward. You've just got to consider a linear system like this. Okay, so the problem is that if you have n images, then this is going to be an n by n system, which is going to be, if n is a billion or something like that, you're in trouble. You've got to somehow invert this. This is going to be a billion by billion matrix that you have to invert. Now, one thing people often do is instead of looking directly at this least squares system, they in fact consider the eigenvectors of the matrix L. Okay, and so the intuition behind looking at the eigenvectors is that the smallest eigenvectors are going to correspond to solutions. The smallest eigenvectors are going to give you a basis which is smooth with respect to the data. Okay, now so here's this. I'm just visualizing here the smallest eigenvector of the graph Laplacian. So you can see it's just a sort of constant offset. So we don't use that one, but you can see the second smallest partitions the data in two, and then the third one sort of partitions it vertically, and so on. Okay, so what we can do is just represent our label function f as a sort of linear combination of these eigenvectors of the graph Laplacian.
Sigmas are normalized to 1, the sum...
Oh, no, sorry. So the sigmas here are the associated eigenvalues. Okay, so you can see that they're sort of getting larger because we're looking at the smallest ones. Yeah.
I'm trying to just to get a feel of the magnitude of sigma 2 and sigma 3.
It's a little hard to sort of get a feel for what really magnitude these should be. Well, it's a normalized graph Laplacian, so that does mean the eigenvalues are bounded to some. Is it 2 or 1? I can't remember which one it is. Okay, so if we make the substitution, if we substitute f for some linear combination of the eigenvectors into the previous expression, we end up with this. Okay, so this is the smoothness term as before. This is just now a diagonal matrix of the eigenvalues of your graph Laplacian. Okay, and if we just take the smallest k of them, just removing the very smallest one because it's kind of a default, it's just a DC term. Then this is the alpha is our sort of vector of coefficients over the eigenvectors, and this is the term which tells us that we want our label function to agree with the labels. Okay, so if we want to solve for the optimal value of the coefficients alpha, we now just have to worry about a k by k system. Okay, so things are better, but of course, how on earth do we find the eigenvectors of a billion by billion matrix if we're dealing with that? So in some sense, it makes things a bit easier in terms of actually solving for the label function, but we have to find the eigenvectors in the first place. Okay, so yeah, just to hammer this point home, if you just deal with the original least squares system, you've got to invert, if you have an 80 million image data set, you've got to invert an 80 million by 80 million matrix. If you want to solve in the eigenvector basis, you've got to diagonalize an 80 million by 80 million matrix. Okay, so both of those are sort of, you might be able to do it for 1 million, but you certainly can't do it for 1 billion images.
Is the number 80 million magic?
Well, it happens to be one of the size of the data set that I'm going to show the thing operating on later. Yeah, okay. So, so what do other people do? So other people who want to use semi-supervised learning, the standard approach basically is to, which is often, there's one of the common approaches called Nystrom. There are many sort of other methods that share this common property where they take the data, they're going to just pick a subset of the data to act as a series of landmarks, solve for an exact solution on this. So typically they're solving for the exact eigenvectors of the graph Laplacian of this reduced landmark set, and then they'll interpolate the other data points back into those eigenvectors, okay? And so the basic intuition here is that they are somehow reducing the amount of data that they have to deal with, solving an exact problem on that, and then figuring out sort of how to, what to do with the rest. Okay? So we're going to do something a bit different. Okay, so that was a sort of warm-up. This is what we're actually going to do. So as I was saying before, there's things like Nystrom. What they're fundamentally doing is reducing the number of data points that they're going to use. So in contrast, what we're going to do is actually think about the limit case as the number of data points goes off to infinity. Okay, so you can think of this now as a sort of continuous density. Okay, and the key sort of selling point is that our approach is going to be, in fact, linear in the number of data points. We're going to have to make a big assumption to make that happen. But instead of trying to solve an exact problem on a small subset, we're going to make an approximation that lets us that makes it linear in n. Yeah. So the basic idea is what we're going to do is think about, if you just consider this little distribution of data here, is that as the number of data points goes off to infinity, we can think about dealing not so much with a discrete set of data, but with a continuous density. Okay, so in this little toy example, we've got a two-dimensional distribution of data. Okay, and what we're going to do is we can write down a sort of an analog, a continuous analog to the graph Laplacian. So what we can do is write down an operator LP, which is going to measure the smoothness of a function f on this density. Okay, so as you can see, it's very much the same as before. You've got this W here is an affinity between 2 points in your density. Okay, so just this sort of Gaussian type affinity, and then you have this term here, which is you want nearby points on your nearby value for two nearby points x1 and x2. They're going to have a high affinity, and you'd like their label function f to be similar. And so what we're going to do is we can look at the eigenfunctions, the eigenfunctions now, because everything's continuous, of this LP of f guy. So just understand what these things look like. So this was the discrete case where we had discrete data, and those were the eigenvectors of the graph Laplacian. So the eigenfunctions of this density are sort of the continuous analog. So this is the density, and these are the functions. Okay, so you can see the second smallest eigenfunction splits the data vertically, and then the third smallest one splits it in the horizontal direction. Okay, so the idea is that as the number of data points goes off to infinity, the eigenvectors in the limit become the eigenfunctions. Okay, now finding those eigenfunctions is what we're going to do. Now, if our density, the data we were looking at, has a nice analytic form, for example, it was uniform or Gaussian, then actually you can just write down an expression for the eigenfunctions. But unfortunately, most real-world data just doesn't have a uniform or Gaussian distribution, so you're in trouble. Okay, and what we're going to do is basically compute a numerical approximation to these eigenfunctions. Okay, so now the key assumption we have to make to be able to do this is that we do have to assume that the input distribution is separable. So that is, in our little toy 2D example here, we assume that we can actually. Whoops, sorry, my slide's slightly out of sync here. Okay, so we're assuming that we can model this as a product of two distributions, one over each dimension. Okay, now. And there is a sort of theoretical result that says that if we can compute the eigenfunctions of each one of these guys in turn, then they will in fact be eigenfunctions of the actual overall joint density, which is what we're trying to find. Okay. Now this is quite a big assumption. Okay, and we're going to come back and revisit that on both toy and real data.
Your formula for the continuous Laplacian already had them in a separable form. Just kind of jumping ahead.
Yes. Thank you. Okay.
On the previous
yes.
page,
Yes. You're right. Yes, you're right. I mean,
they were already separable.
Yes, it's true. It's been written out like that. Yeah.
Okay.
Yeah. Okay. So I think
that's not endemic in the definition of the.
Exactly. Yeah. Exactly. Okay. So let's just consider how we would find a numerical approximation to the one-dimensional distribution, which is going to be the marginal. Let's just consider the marginal distribution for, say, the first dimension. We're just looking at P of x1. So here's up. We've, in fact, got a lot of data points that we assume have been drawn from this density. So if we compute the marginal distribution of this guy, that's what the blue curve is here. And of course, in practice, we don't have this. What we really have is the data itself. And so we can form a histogram. We can put down some bins at a series of discrete locations. We can just see how many data points fall into each bin. And we're going to get an approximate version of this true marginal. Okay? So we're going to have this histogram h of x1. Okay, and then what we can do is we can solve a little eigenvector equation for the values of the eigenfunction at those discrete locations, basically at the centers of the histogram bins. Okay, so and we're going to solve essentially for the value g, which is the value of the eigenfunction, and the associated eigenvalue of that eigenfunction. Okay, and so and you can compute it pretty easily. So P is going to be the matrix which just holds. It's a diagonal matrix which holds the values of the density. So that's just the histogram counts, as it were, or normalized on its diagonals. And these guys here are sort of analogs to the things we had in the original graph Laplacian. So W is just the affinity between the locations in your one-dimensional space. That's just between the different bins. And D is just some sum over the rows of W. And so when we're solving this equation, this is just, remember, in 1D, we're just looking at a one-dimensional distribution. We're solving for G at a series of discrete locations, which correspond to the bin centers, and this sigma, which is the associated eigenvalue. So what are these? When we do that, for example, that distribution, what do they look like? Okay, so this is the first eigenfunction of this little marginal distribution. So this is what it looks like here. So you can see that it changes rapidly when the density is pretty low here, and then it's fairly constant when you actually have high density. Okay, and the second one looks like this, and the third one looks like this. So each of these little circles corresponds to the the x coordinate. It's lined up at the x coordinates of the bin centers. And then so we do that for one dimension, and then we go on to the second dimension. Okay, so this is what the marginal distribution looks like for the second dimension. Okay, it's sort of Gaussian, because in our little toy example. And so the first eigenfunction is pretty linear. Okay, and then the second one's got sort of one kink in it. The third one, and then this third one's got a second kink in it, and so on.
The little red bars in the third one just disappeared.
Oh, you're quite right. There. Yeah, that's cut and paste error, I think, for me. Okay, yeah. Okay. It's meant to be the same distribution for all three. Yeah, thank you, Rick. Okay, so what we've done now is for each dimension we've computed these little 1D eigenfunctions. And so the question is, but if you remember, oh dear, sorry, these things are jumping around. What we're interested in actually is computing the approximate eigenvectors of the graph Laplacian. So how do we go from these eigenfunctions to the eigenvectors? Well, what we do is we take each data point and we simply interpolate it in the approximate eigenfunction. Okay, so this is fortunately a pretty quick operation. It's just a sort of one-dimensional interpolation. Okay, and if we have k of these eigenfunctions we're dealing with, for each data point we have to do this, do k interpolations. So if we have 1 billion data points, we may have to do this many times. But fortunately, it's a pretty quick operation to do. Okay, so that's pretty much the algorithm. Just one important pre-processing step is that we do assume that the data is separable, okay, for this thing to work effectively. And your input data may well not be separable at all. And we use PCA to sort of rotate the data. Now, unfortunately, it would be nice to be able to do other types of mapping to the input data. But the catch is you must preserve the distances, because those affinities all depend on the distances between points. So if you do anything other than rotate, then you're in trouble. And so, well, PCA is one form of rotation. You can imagine other types. But for the time being, we're just using PCA to rotate our input data and hopefully make it more separable. Okay? And so we'll look at that in due course. So just to summarize the algorithm, we're going to take the PCA on take our input data, do PCA on it to rotate it, and hope to make it more separable. And then for each dimension of our PCA data in turn, we're going to construct a one-dimensional histogram, okay, just to get the marginal density. And then we're going to solve numerically for the eigenfunctions and their associated eigenvalues of each of those dimensions. Those funny wiggly green curves I was just showing. And then what we're going to do is we're going to use the eigenvalues we've computed, and we're going to sort the eigenfunctions from all different dimensions, okay, and take the first k. So say you have to decide how many you want to look at. And so maybe make k equals 64 or 128 or something like that. And then for each of those guys, the k eigenfunctions which have the smallest eigenvalues across all dimensions, you're going to take your data and interpolate into those k eigenfunctions, okay? And that's going to give you the sort of an approximate set of k eigenvectors of your normalized graph Laplacian that you can then plug in to that least squares system we were looking at earlier and then solve to give you the label function of your data.
So is k here the number of dimensions on the vector, or it's the first number of eigenvalues?
Sorry, this is true. It's not very clear. So the so k is the number of eigenvectors in your little least squares equation you're going to deal with. So A would be a vector of length k. It's the sort of coefficients on each of those k eigenvectors. So what we've done basically is come up with a scheme for computing an approximation to U. Okay? To assume separability to the data, but is linear time to do it. Okay? Rather than some sort of polynomial type time algorithm for computing the exact eigenvectors. Okay. Okay, so just to do a little comparison here. So in Nystrom, what they do is they'll select a small subset of m landmarks. M is some sort of moderate number. They will compute the exact eigenvectors of that m by m system, or pick the smallest k. They don't need to compute all of them, in fact. And then they will interpolate the endpoints back into those k eigenvectors and then solve the k by k linear system. Okay? And so they're polynomial in the number of landmarks because they're doing this thing exactly. Okay? So even if they use some fancy iteration, it's still going to be at least quadratic in M here. Okay, so with us, we're rotating our points, we're forming D one-dimensional histograms. D is the dimensionality of the input vectors. For each of the D dimensions, we have to solve a little B by B linear system to get the eigenfunctions, and that's tiny because you only need like 50 histogram bins or something, so that's 50 by 50, and then you have to interpolate in your data points. Okay, so this is fast, but it's linear in n, and then you solve your k by k linear system. Okay, so we are linear in the number of data points. Of course, we are making this big assumption about separability of the input data. Okay, so let's look at some toy experiments now. So here's a little grid of data, each element perturbed by a little bit of Gaussian noise. Stick labels on 2 data points and see what happens. Okay, so if you solve the exact least square system, it's a little bit sensitive to the noise. This separating threshold sort of jumps up and down, but you can sort of see, it does roughly the right thing. The eigenvector approach, again, it doesn't quite have this diagonal slant for whatever reason, but it seems to do a sensible thing. It's probably overfitting a little bit the 2 examples we have. And our approach does something reasonable too. Okay, so let's look at these 2 approaches. So this one's using the exact eigenvalues of the graph Laplacian, and this one's using the approximation that we've computed using the eigenfunctions. So if we take a look at the eigenfunctions of that data, so the first one, so let me just get the laser pointer so I can wave. Okay, so this is the smallest one, which is the smoothest. So both of them pretty much the same, and they've got very similar eigenvalues. Second one, again, pretty similar. This one's up, just the sign has been flipped, but it's basically the same shape. Third one is, again, very similar eigenvalues. And here things start to diverge because currently we only consider these eigenvectors. We don't allow any sort of diagonal eigenfunctions, if you like. So in this case here, you can start to see this thing's using both dimensions, and so you get a funky type function here, which has is a smaller eigenvalue than these ones here, which just start partitioning up the horizontal axis more finely.
So you won't take the outer product of eigenfunctions along 2 dimensions?
We thought about doing this. But we're not at the moment.
Okay, that's why I was wondering why you didn't have a k-squared blow-up or k to the d blow-up.
Yeah, that's right. So we've been thinking about sort of ways to sort of compute, sort of combinations, but we've not done that yet. Okay, so now just to look at a little toy data set again, another toy one here. This is some toy data, 2 labels. In Nystrom, you're going to just decimate the data and then compute exact solution on that. And you can see that if you decimate too much, then you end up losing the structure of the data. So the eigenvectors that it computes here are sort of, they do the wrong thing. These red points come across the gap. Okay? So by contrast, our thing, looks at all the data, at least in this toy case anyway, does the right thing. Now, we fall down, in a case like this, we have 2 concentric circles. There are significant dependencies between the dimensions here now. You put a label on the inner and outer circle. Nystrom does the right thing, even though it's got a very small set of data to work with. Our thing keeps all the data around, but then it's done horribly because it just doesn't understand somehow the structure between. It doesn't sound. It's missing the ability to model the dependencies between dimensions. Okay, so this is a slightly sort of philosophical slide. It's really just meant to make the point that it nips. Everyone would have you believe that all your data is like a Swiss roll, okay? And you have these incredibly intricate dependencies that are sort of lapping back on themselves and so on. And I think it's not totally clear that whether you have real high-dimensional data and stuff like that, that it really is like that. I mean, what another sort of plausible model is that you have sort of small cliques of dimensions that are coupled, but then those cliques are sort of fairly independent to one another. So you have these sort of, like a sort of sea urchin, or I couldn't find a good sea urchin, it's a pufferfish, but there are many of these sort of long, heavy-tailed kind of things in your high-dimensional space, and that there isn't this sort of intricate kind of manifold structure, or whatever you want to call it, and so on. So I mean, of course, you can't visualize it, and it's hard to get a feel for it, but yeah, I'm not sure I totally buy the Swiss roll model that all the sort of people at NIPS spend their time worrying about. Okay, so let's look at some real data. What we used here was some images we downloaded from the internet. Okay, so in this case, there's 126 classes. We basically took different nouns, put them into search engines, and got back the images. A total of 63,000 images. And Jeff and Alex Krzyzewski and Vinod Nair at Toronto got people to label these. Okay, so we actually have ground truth labels, which lets us actually carefully assess the performance of our algorithm on them. Okay, and this is part of the CFAR provided funds for the labeling.
Sorry, why are there pictures of clocks in the class called emu?
It's because we just simply put this noun into the search engine, and I'm showing you the raw output of the search engine. Oh. Someone has gone through to label whether these were true instances of an emu or not. So, for example, this would be a negative example of an emu. Okay. Or, yeah, because it's a clock rather than an emu. Okay, and now for each image, we're going to use a very simple representation, but we're not going to work with pixels directly. We're just going to use a single gist descriptor. Okay, so this is kind of like looking at responses of oriented Gabors at different scales over the image. It's kind of conceptually not too dissimilar to SIFT, and it's sort of been hand designed to be a rough. The Euclidean distance between gist descriptors is meant to be a sort of rough substitute for the perceptual distance between images. Okay, so there's no learning involved. It's just some descriptor that someone's cooked up. Okay, and we're going to PCA this down to 64 dimensions to do computer eigenfunctions in. Now, one obvious question is how independent are these dimensions? So if we take the original gist descriptor that was in 384 dimensions, we can form a sort of histograms of pairs of dimensions and look at the mutual information between them to get a feel for how tightly coupled all the different dimensions are. And you can see that there are very significant dependencies going on here in the original gist descriptors. Okay, and so after we do PCA on this, and it doesn't do too badly. It does a pretty good job, in fact, of removing these dependencies. So these are looking at pairs of dimensions in the PCA'd gist descriptors, and you can see that the mutual information scores aren't 0, which would indicate true independence, but they're not too far off. They're sort of fairly small values here, and you can see visually they look fairly symmetric and so on, whereas the original ones weren't. Now, this could be just sort of good luck because we're dealing with sort of images, and images have, we're looking at sort of the gist descriptors kind of like sort of wavelet coefficients, and maybe, it's possible to do PCA on them and make them fairly independent. Admittedly, it'd be nice to try this on sort of more general types of data and see whether you do indeed, how realistic this separability assumption is. Okay, we haven't done that. We're just looking at the gist descriptors here. Okay, so one thing you might wonder is what do these eigenfunctions look like of these PCA gist descriptors? So this is a little visualization here. So what I'm showing you is the eigenfunction which has the smallest eigenvalue up here, and then the sort of 256th smallest one down here. And what I'm doing is I'm just color coding them by the input dimension. Okay, so you can see that the first few ones are sort of almost linear functions of the first few dimensions of your PCA, which have higher variance, so you'd expect them to be more easily splittable. And as you come down here, you can start to see, after a bit, you start getting sort of second-order ones, which are little, ones with little wiggles. Okay, and then down here, you start to see very high-frequency eigenfunctions of these, first few dimensions, the ones up here. And then but you also see now different dimensions. So as you come down here, you can start to see the dimensions of the input space, which had sort of smaller variance, starting to crop up. Okay, so the first eigenfunction in each dimension looks always pretty linear, and then thereafter it starts to have this first order kink, pretty much, and then second two kinks, and so on. Okay. So what we're going to be doing is taking each data point and sort of doing an interpolation in each of these eigenfunctions to compute a sort of 256-dimensional representation now that we're going to use in our semi-supervised learning scheme. Okay, so sorry, just to make clear what each one of these is, this is one input dimension that is bounded between some value x min and x max, and this little curve is really computed basically at the values of the histogram bins in this dimension, and then what you're going to do is take your data point and take your data point and just look it up in this curve here. Okay. So the eigenvalues seem do a good job of sort of picking sensibly across different dimensions. So you can see here it allocates more eigenfunctions to the dimensions with bigger variance, and then the ones down here sort of still get some. It doesn't. We're just using the numerical eigenvalue here to pick the allocation of the different eigenfunctions. Okay, so the task we're going to do is to re-rank the images of each class. So the idea is you're given some set of images, say for the word Airbus, maybe several thousand of them or something. They've been labeled, so you know which ones are labeled or not. And the goal is to sort of re-rank them, but you're going to give the algorithm all the 63,000 images to compute the eigenfunctions of. And then what you're going to do is take a few labeled ones give it a few labeled training examples, and then you're going to propagate these labeled training examples using the eigenfunctions to the remaining set of images for this keyword. Okay, and then hopefully the images which have the highest label value, f, will correspond to sort of better examples of the class. So hopefully improve the quality, as it were, of the images over the original ordering. And just to measure that, we're going to look at plot a recall precision curve and just look at the precision at 15% recall. Okay, and we're going to do this for lots of different classes. I'm just showing you some of them here. Okay, so that was a repeat of this slide, sorry. Okay, so what we're doing here is varying the number of labeled training examples that we use. Okay, so bear in mind we've always got these eigenfunctions that are being computed on all the data, so that data is unlabeled when you compute the eigenfunctions. You don't use labels in any way for it. But you start to add in more labeled examples, and what we're measuring here is the performance in terms of recall, so precision at a certain level of recall. And chance is this line here. So you can see if we take a classic supervised method like an SVM, it horribly overfits the data when we have just a few examples, but then it sort of revives and starts to do pretty well once we have enough training data. Okay, so this is 100 training examples per class or something like that. If we do the exact least squares semi-supervised scheme, you can see it does pretty well early on. Okay, so here it's doing great. Okay, in the sense it's much better than the supervised case because it can regularize its solution using the data distribution. Okay, so this is not using the eigenfunctions. This is just the standard least squares method of doing semi-supervised learning. But it gets too expensive to run beyond a certain sort of amount of data. So the curve stops here. If we try Nystrom, so Nystrom does better than the supervised case, but it's definitely losing quite a bit over the exact semi-supervised scheme. Okay. And then this is our approach. So we seem to do about as well as the exact least squares situation, but then we can continue up. And so just to make clear, so this thing is this one here. You've got to invert, a big matrix. So you're at least squared in the number of data points, and our one's linear. Okay, and our thing goes up, and it starts to be beaten by the SVM eventually once you have enough training data. But you can see you're getting a big win here with small numbers of training images. Okay, and there's a couple other things here. So you can do nearest neighbors here in green, and then you can just do the exact eigenvalues in magenta here. Okay, so one thing you could try is just, if I vary the size of k, that is the number of eigenfunctions I use, how does that affect my performance? So I'm just showing you here varying the number k on this axis. This axis is the number of training examples per class, so that's complete unsupervised, that's bringing in more data. And the color, so the more red it is, the better it's doing. And you can see when you don't have enough, it doesn't do very well. And you can start to overfit. If you have too many eigenfunctions, it starts to degrade performance slightly. Now, one nice feature about this is, as I was saying at the very beginning, you have noisy examples in real data. And you might be able to want to use these in your scheme. And in semi-supervised learning, it's pretty straightforward. So what we can do is just take all the images belonging to a given keyword and just label them as being positive, even though in practice many of them will be incorrect. Okay? And we can take the images from all other keywords and just label them as negative. So in other words, we're just using somehow the label that was from this original search engine. Okay? And we can give we obviously don't trust these labels so much as the actual hand-specified ones. So we give them a much smaller weight. So that value lambda we use, instead of, it's 1/10 of whatever we give a hand-labeled example. And if you do that, you find actually gives you a very nice boost to performance. Okay? So certainly when you've got very little training, very few labeled examples, the noise examples can give you a big help. And you can get a nice red curve lifts up here. Okay? So it clearly helps to have labeled data still, but the noise examples certainly give you a big advantage at the beginning. Okay, so yeah, this is the same thing, but just shown in slightly more detail. So this is increasing the number of classes you have in your data. This is just number of training examples here. Without noisy labels, you can see the performance is fairly weak when you have relatively few examples per class. And when you bring in the noisy labels, suddenly things start to work a bit better. Okay, and so obviously if you have more classes, then it can use the data from all the other classes as a large sort of negative set, which is why you see the performance sort of improving as you move across this graph. Okay, so I'm going slightly ahead of time here, I guess. But so what time did I start, Rick? Oh, okay.
You started right around 1:35.
Oh, okay, fine. Okay, so okay, well, I'm not going to be the full hour, but that's okay. No okay. So anyway, the final thing is we did run some actual results on 80 million images. So it's not 80 million, it's 79 million or whatever. There's about 75,000 different classes. The 126 classes I've just been running this stuff, showing experiments on. This is a subset of the 75,000. And we took all the labels from CFAR that CFAR and Jeff have provided. Okay, so there was about 450,000 of them, of which about 64,000 were positive. Okay, so this is obviously fairly small. It's a big number, but it's fairly small in comparison to this. And what we did is to compute. We took the PCA, took the gist descriptor for each of those 79 million images, PCA down to 32 dimensions, computed the first 48 eigenfunctions of that data. Okay, and so we pre-compute all this ahead of time. Okay, and you end up with this sort of giant 20 gigabyte matrix. Okay, so this is 80 million by 48 matrix. Okay, and then what you can do is you can those eigenfunctions basically being computed on all 80 million. So when you plug labels into some of the points, you can then propagate that label information through effectively you're propagating through the 80 million images, via the eigenfunctions. So this is the kind of result you get here. So this is the raw ranking of the images. You see, here's the what you get with the nearest neighbors, which is just a supervised scheme. Okay, so this is just using a few of the CFAR labels per class for each of these guys. So we give I think 2 or 3 positive and 2 or 3 negative examples for each one of these rows. And then with the nearest neighbors, you can see it does okay. Probably improves things a bit, but you definitely get a better result if you actually are able to use the data density to regularize things. Okay, so both these 2 columns have the same amount of training data, same amount of hand-labeled data. Okay, whereas this one is able to sort of regularize the solution by using the full set of 80 million images. And I should say it's very quick, because once you pre-computed these eigenvectors, all you need to do is just look up the points you want to sort. In this case, we're dealing with just the images from a given word, and then we just need to basically solve a k by k system. So k here is like 256 or no, sorry, 48 in fact. So it takes a fraction of a second to actually produce these results.
So can you go through the 3 columns again?
Sure.
The first column is just what you get out of a search engine.
Yeah, that's correct. Okay, and then what we then do is I've picked rows here for which we actually have labels in Jeff's label set. Okay, and I take for each one of these rows, I'll take maybe 3 positive examples and 3 negative or something like that. Just a few sparse set of labels, and then you can do nearest neighbors. So you could take each image from that keyword. So this was, I don't know, French Spaniel or something, and you would then re-rank it based on how close it was to those 6 labeled examples, and then you do. This is what this column is here. And this column is we're basically solving that semi-supervised learning system using the approximate eigenvectors for those images computed using the eigenfunctions, which were formed from the whole 80 million image set.
So could you, not right now, but if you were reworking the talk, could you show the 3 positives and 2 negatives for each category?
That's true.
Because then we can kind of see visually how similar they are. Like, what's the intuition behind why nearest neighbor is working so-so but not great, and what's going on in the other one? Is it that it sort of finds this connected manifold away from each nearest neighbor that's not obvious in the sort of nearest neighbor just PCA sense, but is somehow more plausible as a chaining? Because isn't that sort of what's happening? You're sort of chaining through sets of neighbors?
That's right, yeah. That's the idea, yeah. That's a good idea. I should have done that, you're right.
In each one of these, it's a binary classification, right?
Well, each image is going to get a number assigned to it by that label function. Okay, so I'm showing you here the ones which have the highest value of that label function. So you have a confidence associated with each one of these. So the one at the top left guy is the one that had the highest value of the label function.
So you couldn't solve this problem by taking all the positive examples from, the ground truth one, and just randomly sampling a lot of false positive, or like a lot of the non-category images, and just use those and actually do like the sampling technique, or do the direct method on that.
You mean just train a standard classifier on that and then try to classify? So the catch is that, there are sort of approaches to semi-supervised learning that try to do this. The problem is, so if you have, this is a slightly toy example, but if you have some sort of elongated structure to your data like this or something, and you have labels just down here, then your classifier will sort of, learn what to do something sensible with this portion. And then you have to sort of iteratively, slowly work your way along this thing until you get to sort of the end, the tip here. So it's true that training train your classifier in each iteration might be sort of linear in the number of examples, but then you may have to do many iterations of it to sort of actually get to the sort of these data points that aren't very sort of close to anything else particularly.
Because they just seem like an intuition. All the problems you had in the beginning were kind of having even, positive, negative. The number of sample, number of points were evenly in the negative and positive, let's say. But if you have, the positive is much lower than the negative. Do you have to do these techniques if you do have a large discrepancy in the number of positives?
You still have this small amount of rather sparse set of positive labels that you have to somehow do something sensible with. It's sure you could declare everything negative, but then you would have, it's not going to do anything useful. So, yes, what Rick's saying is the intuition there is right, so that you're sort of chaining between examples. These eigenfunctions are providing you with some way of propagating those few hand-labeled examples, their label information through the rest of the data. And so, it seems to help over just somehow taking the sort of just using nearest neighbors, but just using the sort of immediate closest examples.
Neighbor, did you specifically remove positive examples, or the first 3 images that?
Yes, I think we did remove the okay, so I guess I've been talking about a semi-supervised scheme that can scale to these really large problems. So essentially, it's linear in the number of examples. So it's feasible to deal on these giant data sets. And so certainly, we've worked on 80 million, but there's no reason why this thing wouldn't work on sort of things of, a billion images or whatever. And so the fundamental difference is rather than subsampling the data, we're just going to think about what happens when you have an infinite amount of unlabeled data and treat it as if it was a density. Okay, but the big catch is that we do make an assumption about the distribution, that it's somehow separable. And yeah, the last experiment was really showing that it's feasible to do this whole thing in a big graph with 80 million images or whatever in a fraction of a second. So that's it. Yeah.
Thank you. I've asked a lot, so you guys go ahead.
So in your toy examples, with the semi-supervised case, you knew that there were it's a two-class problem.
Yeah.
And so in the 80 million web image data set, did you, in other words, like in unsupervised learning, it's a clustering problem because you don't know how many classes there are.
Right.
And in the semi-supervised case, do you find new clusters, or you don't do that in this?
No. So it's exactly how you deploy the semi-supervised learning thing it's true. There are many different ways you can do it. So in the 80 million case, what we were doing was simply to just consider all the images belonging to a single word in isolation. Okay, and then the only external source of information would come from the eigenfunctions, which had been computed on all 80 million, which you can think of as somehow in some way defining a sort of clustering, some sort of clustering basis over the data. Okay. So other than that, we weren't using any other classes. In some of the experiments on the 126 classes, we were using other classes there as negative examples. Okay? So in fact, you can do it with the 80 million. It is a bit slower. I mean, it takes about 45 seconds, but you can actually do a giant thing where you would use all 79 million odd negative examples and just have a few positive examples and run it like that. Yeah, I mean, it is slower because then you really are having to sort of work with matrices. I mean, the matrices get very big. I mean, you have to hold in memory then your entire 20 gigabyte matrix of eigenvectors to do that.
I may be misinterpreting, but on one of the slides you showed that you did better than the exact eigenvector.
Yeah, so that's certainly possible because the exact one is can overfit a bit. It's a bit sensitive to noise. When we were playing around these toy examples,
helping. Is that one way to interpret it? If you assume the data is independent, it is.
Yeah. So in this sort of case here, this exact case is quite sensitive to.
Sure.
I mean, the solution you can get become quite different just if you just generate different random samples here. So I think there's something going on with that. Oh, yeah. No. I know which one you were talking about, but I'm just. At least that's our sort of understanding of. I mean, it's pretty. I mean, it's the same up to noise. I mean, I'm not sure it's really any particularly better.
Like one more time, right? So the pit.
The
exact pink.
So you want to put on the cyan one or the pink one?
Oh, sorry, my brain's switched up. The pink one.
The pink one. Okay, so in the pink one, I think what's happening there is.
This is what you're trying to approximate.
That's right. So what I think's going on? Yes, I think. Well, Yair and me, what we think's going on is that by confining it to just these separable these ones per dimension, it seems it's probably helping because in all these cases we're using the same number of k is the same, so 256 for all cases. So that now it's yeah. So it's. I mean, if you increase the number, if you make k as k goes off to n, then this guy comes up to the cyan one. Yeah, the magenta goes up to the cyan.
Well, it doesn't necessarily converge to the same thing because you're still enforcing separability, and the eigenvector never has separability.
No. This one's the exact eigenvectors.
Right.
But that doesn't have any separability assumption in.
I know, but if you increase n on that, that's not necessarily going to match the performance of your separable thing. It might exceed.
Oh no. I was talking about the least squares case.
Oh.
Yeah, which yeah.
Right.
What's the percentage of samples you use for the next one?
So I did with as many as the computer could cope with, which was I think we had about 5,000 data points here. So what's confusing is here is I've got many different there are many different classes in the big pile of data. Okay, so it's not just like and there's all the test data too as well. So there's a lot of data you actually have to compute. Everything. Well, okay, so over here you've got say roughly 63,000 images, and you've got the largest matrix you could sort of compute eigenvectors in reasonable time was about 5,000, 6,000 size matrix. Well, okay, so I wasn't using all the tricks. You could use some fancy trick to compute eigenvectors of a bigger matrix, it's true. And I mean, there are some tricks for if the thing is, you've got to be a bit careful about assuming, you can't necessarily assume your Laplacian is sparse, actually. Because if you try to sparsify too much, you start ending up with these sort of disconnected kind of islands of points. So if it's nice and dense, then there's lots of sort of bandwidth in the graph for the labels to propagate through. But if you start sparsifying like crazy, then you can start getting these disconnected guys out here who just don't talk to the rest of the graph. So there is a bit of a danger in there's lots of techniques for computing eigenvectors of very large sparse systems and stuff like that. But it's a you don't have to sparsify too much before this sort of thing starts to happen. Jeff. Yeah.
I missed something, which is, are you always just solving two-class problems, or do you ever solve a multi-class problem?
At the moment, we're just solving a two-class problem. Yeah, a whole bunch of different two-class problems, and I'm averaging the performance to show you the curve. Yeah, we have basically more work on doing the multi-class thing. This is where we start considering all classes simultaneously.
So basically, you're taking an approach that is in essence quadratic infinite. They're using lots of clever tricks to try and overcome that, and in essence would like to solve a two-class problem. And if you take a feed-forward neural net with lots of output layers, that's in essence linear, and in essence would like to solve a multi-class problem. So if only you could use the unlabeled data to somehow get the features.
Well, I mean, yeah. Okay. This is okay.
This wasn't really a question.
Okay, no. Yeah, so I guess the point is, your choice of features here. I mean, it's quite a simple scheme that you could plug in. If you learn your features from some sort of deep leaf net or something like that, you could just plug them in, and this would give you a neat way of. The other thing to say is, yes, this ability to sort of weight your examples, according to how confident you are in their label, it's trivial. I mean, it's just you just set the number in the matrix.
The other comment is when you've got unreliably labeled data.
Yeah.
If you train something like backprop with these unreliable labels, it's trying to make the answer fit the label and change the parameters so that its prediction fits the label. And what it ought to be trying to do is first decide whether it believes this label, then decide whether to try.
Sure.
So it really, really, really needs a mixture of, do I trust this label? If you've done a reasonable amount of unsupervised learning, you can just reject a lot of bad labels. And I think in the long run that'll work much better. I think the idea of putting in unreliable labels and saying, sort of, don't trust these much, but trust them all equally.
Oh, I see what you're saying.
Dynamically infer, based on what you already understand, that this is a rubbish label.
Yeah.
We have evidence.
Yeah, no, I know what you're saying.
If you go back to your energy formulation on the very first page, right, that's not sort of built in. I mean, there's a lambda and you trust it. In other words, it's like covariance unmeasured. Sometimes there might be an outlier process.
Yeah.
But as soon as you've got lots of unlabeled data, and if there's natural classes in the data, which there have to be for this approach to be interesting, then you ought to be able to believe some labels more than others based on what the data is.
Right. I mean, in practice, but you sort of see that when you solve the label function. I mean, the guys that are true labels will actually have other points nearby which have the same label, but those ones that are outliers will be way in the space and will have a tiny affinity connecting back to the rest of the sort of guys where the action is somehow. So.
I mean, you could say that this is still intrinsically a least squares formulation, right? Even though, actually in this formula there's nothing saying it's a two-layer problem. You could make y be a multi-valued function. It would just have weird behaviors because it would sort of interpolate between labels, right?
Yeah, so
let's just say it's binary, right? This is least squares, whereas people who do robust stuff will say, well, let's put a robust function over each one of these f minus y things.
Yeah, right? So actually we did try that quickly. At least for our data, it didn't seem to help massively, but it's true, it was all a bit rushed, and we should probably go back to that.
It might depend how noisy your data is, right? If it went through just process, then we assume the labels aren't noisy, right? The humans have vetted those, so it won't make a difference.
That's right. So yes, we do have work where this is not a vector anymore; it's a matrix. Where you have each column's a different class, and you're solving for a matrix F on a vector. I mean, this is our Semi-supervised submission, which someone in this room probably might be reviewing. So I'm not sure how much I should say about this. Okay, so if you're curious to try it out, we've written a little MATLAB version of it that you can try, and it's I mean, it's the same code that we use to run the 80 million images on. So, provided you have enough memory just to hold up one memory, you don't need to do any fancy memory swapping. It's very simple code.
But essentially, like you said, when you summarize the algorithm, first you do a rotation to hope to make it more separable, and then you basically analyze each dimension separately using a histogram function.
Yeah.
And then you just, among those k, you choose k from each dimension.
No. So that's the point.
That's
because you might have one dimension.
Each of your basis functions is a constant along all dimensions except for one, right?
It's constant.
Like you showed in the diagrams, they're basically just one-dimensional functions.
Yes, that's right.
With constants in the other dimensions. You just choose the best ones.
Yeah.
Right.
So there we go. Alrighty.